Okay, as we delve further into the rotational world, it's time to talk about energy. We've converted velocity into rotational velocity. We've converted acceleration into rotational acceleration. We've converted momentum into angular momentum. Now we're talking about angular kinetic energy or rotational kinetic energy. Now, again, let's compare it to the linear world. We know that K is equal to 1/2 mv squared. That's what it's always been. It's going to stay that way. It's not going to change. In the rotational world, K rotational, K rot, if you want to remember it that way. We don't usually put a thing. You could put a L for linear or T for translational if you want, to keep track of it. 1/2. Remember, the linear equivalent to mass in the rotational world is I. I, again, remember, right now is just a number. You'll have to have a formula to calculate what I is. Every shape will have a different I. I is moment of inertia. Tells you how easy something rolls. Times, of course, angular speed, which is omega. Now, don't forget our bridge equation. V is equal to R times omega. That allows you to bridge the two worlds. So therefore it makes life a lot easier. So let's start with something. How about let's take a meter stick. And let's allow that meter stick to rotate that way. And what I want to do with that meter stick is I want to calculate how fast is it moving in the rotational world. In other words, I want to calculate omega when it's at the bottom. So in other words, as it swings down to this point, I want to calculate what omega is going to be. At the bottom, I need to close my parentheses. Well, it's an energy problem. We know that energy has to be conserved. So remember, I'm going to worry about this center of mass right here. It's directly in the center of the meter stick. When it finishes, it will be right here. So if this is 1 meter, this is going to be 1/2 meter. So at the top, up here, all potential energy. Down here, all kinetic energy. But it's just rotating, though. It's not falling straight. So what I'm going to say now is energy before equals energy after that we've done before. At the top, mgh. And at the bottom, we have rotational energy, which is going to be K rotational. The entire meter stick is not falling, so I don't have to worry about that linear velocity. And I'm going to do that. Now let's go through and solve it. And let's do this one in terms of variables. So instead of calling this, yeah, let's do it in terms of variables. Let's call that L. So this would be L over 2. That way it's more generic. Well, that's the mass of the meter stick. G we know is G. Well, the distance it's fallen is L divided by 2. That's equal to 1/2 I. Now, let's leave it as I right now. But I for a rod, and again, you'll be given this, you don't need to know it, is 1/3 ml squared. And again, you don't have to memorize any of those moment of inertia formulas. It'll be given to you. Right now, the moment of inertia is just a number. You just have to calculate it. So let's go through. Again, we're trying to calculate omega. So let's go mg L over 2 is equal to 1/2 1/3 ml squared times omega squared. Let's get rid of, I can get rid of m's like that. I can get rid of one of my l's. Can't get rid of both of them. So I get omega squared. Well, let's slow down a little bit. Let's go over here. We have 1/6 L. That's equal to G over 2. So multiply both sides by 6, and that disappears. Divide both sides by L, and that disappears. I get omega squared is equal to 3G over L. So therefore omega, right off the screen, omega would be the square root of 3g over L. Key thing to do it is that energy before is equal to energy after, but now I've got rotational energy. So let's look at another type of problem that we might encounter with this. Let's take a ball rolling down a ramp. Common type of thing that we might have. I'm going to have it, let's go down this way. The ball is up here. Let's make it a solid disc. A solid disc rolling. Key thing is there's going to be no slipping. And that's a common thing. It's almost like the frictionless type thing that they're going to give you. Now, this has a mass of m and a radius of r. Let's do it in terms of variables. I for a disk is equal to 1/2 mr squared. And again, you'll be given that. Don't have to know that. Just have to be able to use it. Now, let's take a look at what I want to know is I want to know how fast is it moving at the bottom. I want to know v right there. Now, pretty straightforward in the fact that we're going to use energy before equals energy after, except now it's rolling, so we have an extra component that comes in there. Let's real quickly go to this. I'll tell you what, let's change colors to make this show up a little better. Up here we know it's all potential energy, it's all U. Down here I now have two different types of energy. I have the good old-fashioned linear K that I've always had, but I also have some rotational K. And what I'm going to do now is solve that. I'm going to say that, well, at the top, it's U at the top. Everything else is 0. And then down at the bottom, I have K linear at the bottom plus K rotational at the bottom. And then I'm going to attack it, solving it from there. Now, this is MGH. Oh, by the way, we'd have to know this height. So let's say down to the ground that's H. So MGH is going to equal 1/2 mv squared plus 1/2 I omega squared. So that's our basic, that's the physics, to be honest with you. Now it's a matter of calculating what it works out to be. Again, I'm trying to find V, so I'm going to say MGH, let's expand this a little bit, is equal to 1/2 mv squared plus 1/2, well, I is 1/2 mr squared times omega, and here's where that bridge equation helps us. V is equal to r omega, so therefore omega equals V divided by r. So now what I'm going to do is square that and put it in there. I get V squared over r squared. Now I can do some presto changeo mathematical geniusry. That cancels out right there. Hey, there's an m in every term, so m can go bye-bye. So now what I can do is combine like terms, and tell you what, I'm going to multiply by 2. I don't know that it helps me. Nah, don't worry about that. I go GH is equal to 1/2 V squared plus 1/4 V squared. So GH is equal to 3/4 V squared. So to get rid of that, multiply by 4/3, and that gets rid of that. I get V squared is equal to 4/3 GH. So therefore V is equal to the square root of 4/3 GH. So it's a new way to calculate it. Notice how it still does not depend upon mass, but since it's rotating, it's a little bit different than what it used to be. It used to be in the linear world. Let's compare that to linear world. If I just have an object that falls down that distance, let's do this. This is no rolling, just so we can compare them. If I have no rolling, Here I have all U. Here I have all K. I'm going to say that mgh, which comes from that, is equal to 1/2 mv squared, which comes from that. And I get v squared is equal to 2gh. So v is the square root of 2gh. So notice how they're slightly different numbers if we're talking about an object rolling, because now I have an additional energy. Okay, that's enough for now. We'll play with this more in class.